Okay, welcome back, physics friends. I have a fun one for us today. Now, depending on what physics you're in, this might not be useful for you, but it's definitely useful for AP Physics 1, intensified physics, and it all depends on how deeply you go into friction in your regular physics class. So here I have a box, and let's say that the box has a mass of 10 kilograms. And it's going to go on this inclined surface where the angle theta is 30 degrees. Now I know that the coefficient of friction for these two items, when I'm talking about static friction, or the friction that holds an object in place, that coefficient is 0.5. And the coefficient of kinetic friction, or when the box is in motion, is 0.04. And so the question here is, when I put the box on the incline, will it accelerate? Well, we have to do something here because we can't just assume yes. We kind of need to check to see if it's even going to move. Because remember, static friction is so super cool. So if you were to, static friction is super cool because what it does is it's going to start at 0 and it's going to match your applied force all the way up until its maximum value. And then at its maximum value, it says, nope, I'm done. I give up. And it taps out and kinetic friction takes over. Okay? But it can be any value along that range before it reaches its peak. So we have to see what FGX is when we put it on the incline and compare it to the maximum static friction. Okay? So the first thing we need to do, first step, is we need to compare FGX, the helping force, to the force of friction static max. Okay? Because I know that if FGX is greater than the force of friction static max, the box will accelerate. And I need to use mu k. If FGX is equal to the force of friction static max, acceleration is 0 and it won't move. And if FGX is less than the force of friction static max, the acceleration would also be 0. Okay? So I can use this little chart to help me. All right? So what I'm going to do first is I'm going to solve for FGX, and then I'm going to solve for the force of static friction max, and I'm going to compare them. And then I'm going to see what happens. Either I'm not going to have to do anything because it's going to remain at rest, or I'm going to have to solve for the acceleration of the box. Okay. So FGX, remember, if this is my theta here, FGX is opposite the angle. So I'm going to use the sine of theta. So FGX is equal to the hypotenuse, FG, times the sine of theta. Okay. And so that equals mg sine theta. Okay. So FGX is equal to, the mass is 10, 9.8, times the sine of 30. And when I do that math, I get FGX is equal to 49 newtons. So FGX is equal to 49 newtons. Now, I need to figure out the force of friction static max. So that's the force of friction, S max, and that's going to be equal to mu S times Fn. Now you might also know a static friction equation where the force of static friction is less than or equal to mu S Fn. It's always going to be less than or equal to because it exists along that range. Remember, you might have done a lab where you make this graph and it starts at 0 and it goes up to a peak and then it drops down and it goes flat, right? So this whole range in here, that's your static friction ranging from 0 to max. And then this part here is your kinetic friction. Okay? And so that's how that graph sort of plays into this. So when I look at mu s, I know that's 0.5, and Fn, well, I'm on an incline, so that means that Fn is equal to Fgy. So Fs max is going to equal 0.5, and then Fn is Fg, or mg. And that's the adjacent side, so that's the cos of theta. So this is 0.5 times 10 times 9.8 times the cos of 30. And when I solve, I get it's 42.4 newtons. So that's what my friction, the maximum value my friction can be. So now I'm going to compare these two. How does FGX compare to FS max? 49, 42.4. Well, it's greater than. So I'm going to look back up here at my chart and I'm going to say, well, FGX is greater than FS max, so this box is going to accelerate. It tells me that the X component of the weight is greater than the amount of static friction that it can put out. And so the FGX is going to pull the box. It's going to overcome static friction and it's going to pull it down the incline. Okay? So that means it's going to accelerate. I need to use the kinetic friction and I can figure out what the acceleration actually is. So now I'm going to go to my F net equation. I'm going to go F net equals ma, and I'm in the x direction again. And F net is helping minus hindering. So helping is, if it slides down the incline, it's the orange arrow because it's pointed parallel in the same direction. So that's FGX. And hindering would be friction. Now be careful, it's not static friction because it's going to move. It's kinetic friction. So this is minus the force of friction is equal to ma. Okay. Now FGX I already found, it's 49 newtons. And, oh, I don't even need to do that. Check this out. I'm just going to rewrite it as mg cos sine theta minus mu k mg cos theta equals ma. Now I'm not going to worry about that effect that I already calculated 49. You can, but this actually is a little bit easier because I'm going to divide by m to figure out the acceleration, and because m is in each term here, I can drop m out of the equation. So my equation turns into g sine theta minus mu k g cos theta is equal to the acceleration. Okay, so this would be 9.8 times the sine of 30 minus 0.4 times 9.8 times the cos of 30 is equal to a. And I get 4.9, because the sine of 30 is 1/2, minus 3.39 equals the acceleration. So a is equal to 1.5 meters per second squared. And that is my answer. All right. Now this problem could have gone in lots of different directions. If the force of static friction max was equal to 49 newtons, well, it wouldn't accelerate. It would remain at rest. They would be equal. And if the force of static max was larger than FGX, it would also remain at rest, which means that you could lift that incline up more to see where it's just going to slip and start to move. Okay? So that's a fun problem, and hopefully I'll see you in the next video.